Let's talk about one more property of graphs, that is coloring. Okay, so we'll see this coloring concept. What is coloring is assigning every vertex a color so that no two vertices which are adjacent should get same color. Okay, so I will explain this with example. Consider this graph A, B, C, D. So coloring is nothing but for every vertex you should give a color. So generally colors can be, maybe characters, otherwise you can give numbers also. But so that no two vertices, no two adjacent vertices should get same color. Example, if you give color 1 to A, then don't give color 1 to B. That means you have to give a different color. Now for C, don't give color 2, but you can give color 1 because A and C are not adjacent. Similarly for D, since it is adjacent to A, don't give color 1, but you can give color 2 because D and B are not adjacent. Okay, finally in one line, no two adjacent vertices should share color. Okay, apart from that everything is possible and every vertex should get definitely one color. So we'll see one more example. So this graph is relatively smaller graph than this one, right? With only three vertices, 1, 2, 3. Then how many colors, required to color this graph? We'll see. I'll give red color to, let's say, vertex 1, and since 1 and 2 are adjacent, definitely we need a different color, let's say green. For 3, since it is adjacent to 1, adjacent to 2, definitely we have to give one more color, let's say yellow. So here three colors are required because these three vertices are mutually adjacent. From now onwards, you remember, any graph has, this kind of substructure like this, then definitely such graphs require at least three colors. Okay, so this is about graph coloring definition or introduction. Now we'll see one more concept called N-colorable graph. Okay, so what is N-colorable graph? N-colorable graph is nothing but a graph which can be colored with n colors. Okay. Example, this graph, you see, it can be colored with three colors, isn't it? That's why this is a three colorable graph. Okay. Now, this graph can be colored with two colors, isn't it? So that's why that graph is called two colorable graph. Now, let's take one more example. A, B, C, D, E. Let me color it. Like I give color 1 here. Since AC are adjacent, we should not give same color. Then let me go for 2. Otherwise, what I do is, for safe side, I give every vertex a different color. Still it is possible. So in the fundamental definition of graph coloring, which is not mentioned is, only one thing is mentioned, no two adjacent vertices have same color, but nothing is mentioned like we have to save the colors. You can give any number of colors, not a issue. That's why I have used 5 colors. Now in this graph, since you used 5 colors, this graph is called 5 colorable graph. So this is the basic concept of graph coloring and N-colorable, concept. Now we'll see minimum number of colors required. So that is denoted by chromatic number of the graph. Chromatic number of the graph is minimum number of colors required to color this graph. Okay. So minimum number of colors. So is there any formula to find out the minimum number of colors in a graph? No, there is no simple formula, and coloring problem is very difficult problem. That means finding minimum number of colors required to color the graph is very difficult problem without checking all possible things, like try, example, this is a graph. So try with color 1, try with 2 colors, try with 3 colors, in that way. Try all possible ways. Okay. So based on that model only we can find out the minimum number of colors. Okay. Without checking that. Example, you did not try coloring this graph with 2 colors. Okay. You did not try. Then you can't guarantee whether we can do it with 2 or not. Okay, that's why we have to try with 2 colors, after that 3 colors, after that 4 colors. In that way we have to try every possibility in the worst case. Okay, then only we can decide. That's why coloring problem is known as difficult problem. Okay, now what is chromatic number of this graph? What is that minimum number of colors required to color this graph? Formally I define chromatic number like this. Chromatic number of G is nothing but it is minimum value among all n's where for n your graph is n colorable. Okay, whenever your graph is n colorable, okay, where G is n colorable, then pick that n and you will get so many n's, right? Example, this graph is 5 colorable and this graph is 4 colorable. That means with 4 also I can color it. This graph is actually 3 colorable. You try it, then you can get it with 3 colors. So whenever I write this part, that means whenever your graph is n colorable, take that all n, like 3, 4, 5, right? So your graph is 3 colorable, pick 3, 4 colorable, pick 4, in that way 5 colorable, then pick 5. Out of them you form a set now. Okay, so the meaning of this entire thing is, forming this kind of set. After that, see min function. If I apply min function, min of 3 comma 4 comma 5 is 3, right? That's why this graph is 3 colorable. Understand? I mean, sorry, this graph's chromatic number is 3 because we tried coloring this graph with all possible colors like 3, 4, 5, but this graph cannot be 2 colorable. If this graph is 2 colorable, then 2 comes into the picture and chromatic number will become 2. Okay, so that's why minimum number of colors required to color this graph is 3. Understand? So we'll take one example and we'll try to color this with a very less number of colors. Example, let me take a complete graph like this. Okay, what is the chromatic number of this graph? We'll see. Okay, let's, and this is A, this is B, this is C, this is D. Okay, I start here. I give color number 1. Since B is adjacent to A, definitely we need different color than 2, right? Then what about C? C is adjacent to A, adjacent to B, then we can't share the color, we have to use a different color, 3. Now D is also adjacent to all the previous vertices, then it needs different color, right? So 4. So without 4 colors you can't color this graph. So minimum value is 4 and 4 is sufficient. That's why chromatic number of this graph is 4. Okay, so no one can color this graph with 3 because so sharing is not possible because everyone is adjacent to everyone. Then you can't give same color to reduce the colors. We have to give same color to 2 vertices, which is impossible because in complete graph every 2 vertices are adjacent. That's a problem. Okay, so in that way, so we can understand this coloring. Let's see some more details about coloring. So first we see chromatic number of cycle graph. Let's begin with cycle graph with 4 vertices. 1, 2, 3, 4, right? This is cycle graph. So I give red color here. Since 1 and 2 adjacent, I alternate it. Then that means I give green color. So here, now these two are not adjacent, I share the color red. These two are not adjacent, I give green. So 2 colors are enough. Just I am observing. Let's take 5 vertex graph, which is cycle graph C5, and let's observe it. So here I give color 1. Here I give, so I use colors and numbers interchangeably. Okay, everything same. Color is a symbol and number is also symbol. Okay, so whenever I say color 1, that means it's one of the color, like so 1. So here I give 2. Then here I can share the color 1. Then 2 can be shared. Then here, since now this point is adjacent to 1 and 2, now I must use one more color, right? So that's why it is 3. Now 3 colors are required. So for cycle graph it is 2. Let's observe one more graph. This time 6 vertices. 1, 2, 3, 4, 5. Let's say 6, right? 1, 2, 3, 4, 5, 6. Let's use colors now. Red color. Here share it. Use different color. Green. Now share it. Red. Share it. Green. Now again share. Red. Now green. You see, I can use alternatively red and green. So just 2 colors are required. So what I understand is when n value even, you are getting only 2 colors, and when n is odd, you might require one more color, 3 colors. So answer either 2 or 3. You don't require more than that because we are alternating the colors. Now chromatic number of cycle graph is 2 or 3, right? Particularly I can say like this: n minus 2 into n by 2 plus 2. So how this formula gives correct answer, we'll see. When n value 4, so what happens is this n by 2 will be 2, right? So 4 minus 2 into 4 by 2 is 2. 2 to the 4, 4 4 cancelled, and you get this 2, which is correct answer. When I take n value odd, what happens, we'll see. When n is odd, example n value 5, formula will be like this, 5 minus 2 into, so floor of 5 by 2. So floor of 5 by 2 is nothing but, integer 2, right? 5 by 2 is 2.5, floor of 2.5 is 2. So 5 minus this will become 4. 5 minus 4, 1. Always when n is odd, the difference between n and 2n by 2 will be 1. So 1 plus 2 will become 3 and it will match for this odd graphs, right? So finally answer is n minus 2 into floor n by 2 plus 2 I can say, right? Now we'll go to these statements. Every bipartite graph is two colorable. Why? Think about it. Second one, why every two colorable graph is bipartite? Stop the video and think for some time and continue the video. Every bipartite graph is two colorable. Why? I will tell you. First, take a bipartite graph. Whenever a graph is bipartite, you can see partitions like this. Example 1, 2, 3, 4, 5, 6, 7, 8. Okay, these are all vertices. 1, 2, 3, 4. These are all 5, 6, 7, 8. Other set of vertices. Let's say since it is bipartite, I can partition like this, right? This is partition A, this is partition B. Now, what I do is, since I know that there is no edge between 1, 2, 2, 3, 3, 4, so on, then I can share the color. I give red color here. Okay. Now, since all 5, 6, 7, 8, doesn't have any adjacency, then I can give a different color called GGG. There is no problem, isn't it? Now, see, with two colors, I colored any bipartite graph. That's why every bipartite graph is two colorable. That means we can color it with two colors. Second one, every two colorable graph is bipartite. We'll see why every two colorable graph is bipartite is. Let's take a two colorable graph first, because they are talking about two colorable graph, right? So that's why we have to take a two colorable graph. Let's say you have a graph like this, because we don't know what is that graph structure. Then we can see, two colors in the graph. One is color 1, let's say, second one color 2. Since it is a two colorable graph, right? So let's say really it's a two colorable graph, then I can color it with two colors. Let's say already I colored it. In such graph is bipartite. Why? Take two partitions. Okay. So I am forming bipartite graph, you see. One is partition A and second one partition B. In partition A, you keep all the color 1 vertices. Since all that color 1 vertices doesn't have any edge, if they don't share edge, right? Example, they are A, B, C, D, E. They never share an edge. If they have an edge between them, how it will be, how can you give same color? You gave same color means definitely they don't have any adjacency. That's why happily I can keep everything in one partition. Now all the color 2 vertices can be kept in another partition, like maybe F, G, H, I, J, so on. Again, I can prove that there is no adjacency between these two. If there is adjacency between these any two color 2 vertices, then how can we give the same color to them? That is impossible. That's why they don't have any edge between them. Then we can keep in another partition. That's why every two colorable graph can be partitioned like this. So finally we prove that every bipartite graph is two colorable and every two colorable graph is bipartite. So the same thing can be written like this. Okay. What I can do is I write like this. A graph is, because it is two directional, you see, I proved two directions. I took bipartite, I proved two colorability. Then I took two colorable graph and I proved bipartite. That means a graph is bipartite if and only if, whenever you know that some statement is true for two directions, we write like this. A graph is bipartite if and only if it is two colorable. That is what final meaning, right? So this is what we proved. Understand? Now we'll see one more example. So here I would like to discuss about some facts about coloring. Okay. So fact number 1 is chromatic number of any graph should be less than or equal to V, where V equal to the total number of vertices. Let me write mod V. Okay. So that means minimum number of colors required to color any graph cannot be more than number of vertices. That's very obvious, right? Why? So why we require, because for every vertex we are giving at most one color. If there are 10 vertices, then any graph requires not more than 10 colors, right? No graph requires more than that. That's why chromatic number of any graph will be definitely less than or equal to V. Second one, if some subgraph requires k colors, then definitely chromatic number greater than or equal to k. Example, you have a graph and that this is, let's say, subgraph. If this subgraph chromatic number, what is chromatic number? Minimum number of colors required to color this subgraph. Okay, so minimum number of colors required to color this subgraph is, let's say, something k. Okay, that means if some subgraph requires k colors, so he is not talking about minimum number, but definitely this subgraph requires at least k colors, then chromatic number of whole graph definitely greater than or equal to k. Even this part requires k colors. To color overall graph, you need either k, otherwise more than that, right? So if you can do with less colors, like less than k colors, let's say if you can do it, then let's say k value 10. Then if you can do with 8 colors, that means you are coloring entire graph with 8 colors, then this subgraph is now colored with 8 colors, not more than that. But already we know that you can't color this subgraph with 8 colors because minimum colors required to color this one is k. That is what given. That means if some subgraph requires k colors, then supergraph requires at least k colors. That's why its chromatic number, minimum colors required, is definitely greater than or equal to k. One more fact we'll see, that is chromatic number of any graph is equal to maximum of chromatic number of C, where C is connected component. I'll explain this statement. Example, you have some components in your graph like this. Okay, now like this. This is component number 1, component number 2, component number 3. This overall entire thing is your graph. This is your graph. What is chromatic number of this graph is the question. The fact is, the chromatic number of this overall graph is, like example, this C1 requires 3 colors. That means minimum number of colors required to color this graph is, let's say, 3. Minimum number of colors required to color this graph is 2, right? And minimum number of colors required to color this graph is 3. So I write like this. Chromatic number of C1 is, let's say, this one. This is chromatic number of C2, which is 2. Chromatic number of C3 is nothing but, let's say, 3. Then you don't require 3, 2, 3, overall 8 colors. Okay, so what I do is I find out the maximum chromatic number of these components. Okay, example here, maximum coloring number is 3 for this component. Then I take 3 colors, let's say red, green, yellow, then I can color it. Okay, because 3 colors are enough. Then with that 3 colors I color this graph also, because there is no adjacency between these two. Whatever the way you color this graph, then there will not be any problem with this component. Similarly, I can color this graph independently without seeing these vertices, because there is no connectivity between this component and other components. So what I want to say is, if you have 3 colors, happily we can color this one, this one, this one. Okay. Example, let's say there is one more component which requires 7, then overall you require only 7 colors. That is what this statement says. So finally, chromatic number of overall graph is maximum of all the chromatic numbers of individual components, where C is a connected component. Okay, so take every component and find out chromatic number. Out of them, get the maximum one. Example here, 3, 2, 3. If you have another component whose chromatic number, let's say, 7, that means minimum colors required to color this component is 7. Then overall you require 7 colors. Okay, not more than that. That is what this fact. Okay, so these are all about facts about coloring.